Okay, so we're going to do community detection algorithms. So again, what a community is, in common sense, community means what? A group of people getting together, they talk more with each other compared to talking to outside the community. So from a graph theory point of view, you have basically a group of vertices such that you have more edges between the vertices within the group compared to edges outside the group. So it has, say, here, let me show the other graph first. So let us say you have a graph like this. So it's very obvious that we have three communities. One is a community of all these green colored vertices, and then the blue ones, and then this orange ones. So you have more edges among vertices within the community, and few edges outside the community. So that's what you typically expect of a community. Okay. So if you have more edges between two communities, they might as well as exist as one single community, not as two separate communities. Okay. So later we'll see, or even just after, so soon we'll see how to capture what is called the inter-cluster density and intra-cluster density, which means like density within the cluster and outside the cluster. Okay. Now in real-world networks, also communities are visible. So this is like a karate club network. So you have, say, here two communities of people. The blue colored ones, so they talk more with each other, and then this orange colored ones, they talk more with each other, and there are a few edges between those two communities. Okay. So communities could exist in different domains. Like in social network, it's very common. Okay, like in Facebook and all, you can have communities of people. Also, like in metabolic networks. So depending upon the functionality of the entities that are part of those networks, you could have groupings. Okay. Then citation networks, say you can group researchers based on the topic they're working on, and so on. So it is very common in different domains. Okay.
So what is community exactly? Like a group of people similar, like?
It could be, okay, so we could do we could do community detection based on two approaches. One is without knowing anything about the people, just based on the links, okay, between the nodes. So that's based on the topographical information, that's what we call it. The other is based on the offline additional information you know about the nodes, like whether they are from the same region or they speak the same language and so on. Whether there could exist communities between those people. Okay. So we'll first focus on, most of the module will be focused on doing community detection without knowing any offline information, because that is more common. Okay. It's very difficult to gather information about nodes. And later we'll see how to do community detection if we know something more about the nodes. Okay, like for example, there is a male, female node, and so on. Okay, we can do community detection like that. All right, so the one we are going to see, and even some more approaches, could also be used to evaluate how good are the communities that we find with using those algorithms. Okay, so there exist different algorithms that can be used to determine communities in networks, and not all algorithms will be the same result. Okay, some algorithms may give, like later we'll see an example where the same graph you could find different communities based on the algorithms we use. So one algorithm may partition the graph into two communities like this, and another algorithm may partition the graph into two communities like this. We already know one approach to evaluate how good is the other communities. What is that? Using the modularity score. Remember we did for the eigenvector based community detection. So actually we already saw one community detection approach, the eigenvector centrality based approach. Okay. So for this kind of partitioning, the modularity score came out to be 4.63, and for this one it is 5.54. So obviously larger the modularity, the better the partitioning. So This is a better partitioning of the graph into communities compared to this, because you can see there are more edges within the community and relatively less edges between the communities. Okay. So the other approach is to use this density thing, which is not that common, but it's good to know that the density within a cluster is going to be high compared to density outside the cluster. So all the terminologies are interchangeably used. Cluster, community, the grouping, they all mean the same, partitioning and everything. Okay. All right. So let us see how to get what's called the internal density within a cluster. So all you have to do is find the degree for the vertices how many vertices within the community they are connected to. So this vertex is connected to 3 other vertices within the community. Now this vertex has 4 edges, but only 3 of them are 2 vertices within the community. So you have to consider only those 3 edges, 2 vertices within the community. And then again, this vertex has 4 edges, this has 3, and this has also 3. Like, once you find that these are the 3 communities in this graph, find the edges. So you're trying to find what's called the internal density within each community. So you need to find to which vertices within the community the vertices are connected to. So this vertex is connected to 3 other vertices. All the 3 are within the community, same color. So we can consider that as part of the degree. Whereas this vertex has 4 edges, but only 3 of them are 2 vertices within the community. So you have to consider only 3 as a degree for this computation. Then 4, 3,
the
3.
middle one, okay, yeah, got it.
Okay. So the average of this, which is like 3 plus 3 plus 3 plus 3 plus 4, it's not the average. So you have to sum all the actual edges, that's the numerator, divided by the maximum possible number of edges. So you have 5 vertices totally. If each of those 5 vertices are connected to the other vertices, how many edges you would need to connect each vertex to the other vertices? 4 other edges, right? So you need 1 edge to this, 1 edge to this, 1 edge to this. There is this edge that is not there, right? So you need 4 edges to connect each vertex to the other vertices. How many vertices are there? 5 such vertices. Clear? So you divide the numerator, which is the actual number of edges, divided by the maximum possible number of edges. Okay? So that is the fraction. So the internal density and external density are both going to be fractions, 0 to 1. So if they're closer to 1, it means what? You have all the possible edges that could exist there. So you're dividing by the maximum possible number of edges. So if the fraction is 1, it means all the edges that could exist actually exist. So the fraction will be 1.
In the numerator, you need like all degrees, all the edges.
All the existing edges.
Yeah, sum of all. And on the denominator, like 5.
The maximum possible number of edges. You have 5 vertices within this community.
Yeah.
So if each vertex is connected to every other vertex, you need 4 edges for each vertex.
Okay, yeah.
So that is 4 times 5.
Maximum.
Is it clear?
4 times? Okay.
4 times 5, isn't it? You're considering the edge from each vertex point of view. Because the numerator, you counted each edge twice. You see, this edge was counted twice, once from this vertex point of view and once from this vertex point of view.
Yeah.
So you have to consider the denominator accordingly. Okay?
Yeah.
Is that clear?
Except the which we are considering, except that
Every other
is
vertex.
minus 1 just.
Yeah. So that's the formula actually.
Yeah.
Okay? Alright, let us do for this community. So you have, so just based on the graph, compute, you can say that's called the internal degree. So this, what we came up with these numbers, would be called the internal degree. Why they can be called internal degree? Because these are degree, the number of edges connected to vertices within the community. Okay. All right. So let us compute the internal degree for the blue vertices here. So 1, 2, 3, 4, right? Because this edge is to something outside the community. What about this vertex? 1, 2, 3, 4, 5, right? 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Isn't it? So just count the number of edges to vertices within the community and sum them up. So it is 5 times 4.
Sir, did you take adjacent edges?
What?
Did you take adjacent edges?
What adjacent edges?
Like how you got 5, 4?
Okay, so let us pick up this vertex. You have 1, 2, 3, 4. So these 4 edges are 2 vertices within the community.
Okay. Are not they adjacent?
What do you mean by adjacent?
Like.
So from this vertex point of view, it has totally degree 5 because it has 5 edges, but only 4 of them are 2 vertices within the community. So that's called the internal degree. Okay? So compute the sum of all the internal degrees divided by the maximum possible number of edges. Okay? So you have 6 times, there is some typo here, I'll figure out later. So this is going to be 5 times the 4 such vertices with internal degree 5 plus 4 times 2 vertices with internal degree 4. This divided by, you have totally how many vertices? 6. So multiplied by 5. So that is its internal degree. Okay? So I'll change the numbers here. Is that clear? Now what about this community? You have, what are the internal degrees of the vertices? 3 here, 3 here, 3 and also 3. So it's going to be 3 times, also 3 plus 3 plus 3 plus 3, 4 times 3, right? So that is going to be 1.0. So this number is right. Is that clear? Okay?
I'm just scratching my
No,
back.
it's fine?
No, I know it's.
Okay.
You explained it very well.
Okay, good. All right. Any question? So that is internal density. So same thing with external density. So external density, let us wait for this cluster.
So what is internal density? What is external? The lines which are connected to outside.
Yes, so that's external. Okay, so let us see how to do external density. Okay, so internal density is just counting the internal degree. Now, external density is again, okay, so calculated for every community. So if you look at this community, it has edges going out to other communities. So this is one edge that goes out. This is another edge that goes out. So there are 2 edges going out, right? So if you notice here, each edge is counted only once. This edge is counted only once. So it is 1 plus this edge, 1 more edge. So each edge is counted only once. Unlike the internal density calculations where each edge is counted twice. Isn't it? So when you divide this by the maximum possible number of edges as usual, so this is the actual number of edges, maximum possible number of edges, you have to again consider what? So there are 5 vertices the maximum possible number of edges is going to be 5 times 4, but this is going to be divided by 2 because, or you can put it like this. Why it is, okay, like this. 5 times 4 multiplied by 2. Okay? So, this is going to be 2 divided by 20 times 2, so that is whatever the value is the external density, 0.05. Okay? Because each edge is counted only once, we have to divide by 2. Okay? Now again, from this community point of view, you have one edge going outside, another edge, and then 2 more edges. So totally 4 edges to outside other communities. Divided by the 6 vertices, so 6 times 5 multiplied by 2.
Sir,
Yes.
can you please explain that again? 1 plus.
Okay, so you have one edge, another edge,
Yes.
third edge, fourth edge. So 4 edges to other communities.
Okay.
So the numerator is going to be 4. Okay. Divided by the 6 vertices as usual. So 6 times 5. Multiplied by 2 to account for the considering on each edge only once. So in the previous case, in the denominator, we did not multiply by 2. So here we have to multiply the denominator by 2 because we are considering each edge only once in the numerator.
For first one, what you did, like one.
For this community, how many edges are going outside?
5.
Huh?
5.
To outside, 2. So that's the numerator, 2.
Okay.
Divided by, we are considering from this community's point
Five.
of view. So there are 5 vertices. So 5 times 4 times 2.
Why 2?
Because we are considering each edge only once in the numerator. So to account for that, we need to.
Each time.
Yes.
Got it.
Okay.
But the second one.
Second
4.
one, again, just look at this community's point of view. How many edges are going
4.
outside?
4 by.
6 vertices.
Five.
So 6 times 5.
Yeah, got it. But it should be like 4 times, right? It has 4 vertices.
This community has 4 vertices.
Means like the outside lines. I'm talking.
No, you are still looking at this community's point of view.
Uh-huh.
So we want this ratio to be as small as possible. Okay?
No, I'm asking over there you said like 2 into 6 into 5. So why 2? Why not like the previous like number of lines, external lines? You take it. So I'm asking.
Yeah, I understand, but we don't know how many, like in other communities, how many vertices are there. We don't know that, so we cannot use that as a measure in the denominator. We are looking from this community's point of view. So in this community, we know there are going to be 6 vertices.
Yeah.
So that's why in the denominator we use that.
I know 6 into 5. What? Why 6 into 5? I am asking about 2, that particular 2.
Which 2?
2 into 6 into 5.
That's what I'm telling. So that 2 is because we are considering, see, when we did the internal density calculations, we added up the internal degree. So this is degree 3, this is degree 1, again 3 and so on, right? So each edge was counted twice there.
Oh, okay. Oh, okay.
Whereas here, and we did not do anything multiplying by 2 the denominator.
Yeah, why?
Because again, the denominator we had, when you do what, 5 times 4, it means like this edge, so you have 5 vertices, right? So this edge is, you need 4 edges to connect this vertex to.
Okay, each individually. That
Right.
is, and here we
Then you counted like what? To connect this guy to the other vertices. So each pair you consider edges twice. So that's why it balanced. Whereas here, since we are considering each edge only once, the numerator, right? We balance it. Okay, so last community. So you have again 2 edges to outside communities. So you have 2 in the numerator divided by 4 times 3 times 2. So that's going to be the external density. Okay? So we want the external density to be actually low, closer to 0, because that's a good measure of partitioning. We don't want the external density to be high, because if external density is high means what? The numerator is high. So numerator is high means you have more edges to outside communities, to other communities. We don't want that. Okay? So you would prefer the internal density to be closer to 1 and external density to be closer to 0. That's the way we prefer the values to be.
Is there any chances that external density will be -0?
No, there is the chance of getting a negative value. It could be 0, but it cannot be less than 0. Okay? There's no minus term here, so we won't have less than 0. Okay? Looks like okay, accounting him as students. So looks like the class is full today. But still you're missing one student who is still registered for the class. That's okay. Alright, so now we are going to look at some community detection algorithms. We saw already what? The eigenvector based approach. So we are going to see the other 4. So the last one, the homophily, is based on some offline information. Like homo means what? Similar, phily means liking in biology, right? So similar people like to stay close to each other. So that means if you know some additional information about the people in communities, like typically social networks, we'll try to see whether similar people exist as one community, whether there are more edges between them compared to other people. So the other 3 approaches do not use any offline information, just they're only topology based, so just based on the edges between vertices. Okay? And so we already saw this modularity based approach that could be used to calculate how good is a partitioning, right? So again, how it is calculated: for every pair we compute this modularity score. So it is either 1 minus or 0 minus. So 1 minus if you have an edge between the 2 vertices, 0 minus if there's no edge. So what is this di dj? It is the degree of the 2 vertices divided by 2 times m is the number of edges, the total number of edges in the graph. So let us go through the calculations one more time to make sure everybody knows this. So again, for this particular topic, assuming that there is some community detection algorithm that has been run and it has determined some communities, we are just evaluating how good is the partitioning into communities. Okay. So the larger that modularity score, the better the more effective or good the partitioning is considered. Okay, so we'll take this graph and let us assume that some algorithm has partitioned this graph into 2 communities like this, and some other algorithm has partitioned the same graph into 2 communities like this. So we want to decide whether this partitioning is good or the previous partitioning is good. Okay. So what we need to do is find the modularity score for each community. So I gave you that jar file program where you can run it and get the pairwise modularity scores. So pairwise modularity score means for every pair of vertices you can get the modularity score. Okay. So let us compute the modularity score for each community. So this community has vertices 1, 4, 5, 7. So once you know what vertices are part of a community, find the modularity scores for each pair from the output that you get and just sum them up. Okay, so just to know how to do those calculations. So you need not know, you have already the program to do it, but just to know how the calculation is done, for any pair it is either 1 minus or 0 minus. So 1 minus if there is actually an edge between them. So this pair 1, 4, they have an edge between them. If they don't have an edge between them, like 1, 5, they don't have an edge between them, so it's going to be 0 minus. So this second term is going to be, we have to multiply the degrees of the two vertices, looking at 1 and 4. So the degree of 1 is 3, the entire graph. It is 3, the degree of 4 is 4. So it is 3 times 4 divided by 2 times, what is this, 15? 15 is the total number of edges in this graph. Okay, so again, how to get the total number of edges? You could manually count the total number of edges, but you may make a mistake, right? So what's the other approach I suggested you could do to
total degree, sum of the degree by 2.
Okay, so as we just discussed, when you add up the degrees, each edge is considered twice. So add the degrees of all the vertices, divide by 2 to balance for counting each edge twice. So that's why. So if you do that, you could get 15, the total number of edges in the graph. So sum of all the degrees divided by 2 will give you the total number of edges. So, and it has been also proven that if di is the degree of vertex I and dj is the degree of vertex j divided by 2m, this is going to be between 0 to 1. Okay, so the second term is always going to be between 0 to 1. So you have a 1 minus, so which means it's always going to be positive or 0 or positive modularity score. It's not going to become negative. If the pair has an edge between them, the modularity score is always going to be positive. If the pair does not have an edge between them, then the modularity score is going to be negative. Why? Because you do 0 minus something. So 0 minus something from 0 to 1 is going to be some negative fraction. So if the pair does not have an edge between them, they are going to have a negative modularity score. So for this community 1457, if you look at the modularity scores, there are some positive, some negative. So actually having some negative modularity scores is not a good sign for a community, because what does it mean? 1457, they have only these 3 edges among themselves. These 3 edges which are supposed to be there are not there. So that is, so the overall modularity score for this community is the sum of all the pairwise modularity scores. So the negative scores really pull down the total modularity score for this community. If all the pairwise modularity scores are positive, the sum is going to be larger. On the other hand, if some are negative scores, it's going to pull down the overall sum. Is that clear? So for this community, the total modularity score is 0.23. Okay. So similarly, we can do for 2, 3, 6, 8 by getting the pairwise modularity scores. The sum of them is again 0.23. It just happens to come out like that. It may not be the same. So the total modularity score for the partitioning is the sum of the 2 community scores. So 0.23 plus 0.23 is 0.46. So now we need to compare this score with what you could get with the other partitioning. So this is some other algorithm.
So can you go with the last ones? Over there, 1517. Okay, good.
Okay. So some other algorithm has determined these communities for the same graph. So let us see how good is this partition. So one community is 1, 2, 3, 4. So you have 1, 2, 3, 4. So again, consider all the pairwise modularity scores. So you have edges between 1, 2, 1, 3, 1, 4, 2, 3, 3, 4. The only pair that doesn't have an edge is 2, 4. So that has a negative modularity score, the others have positive. So the sum is going to be relatively larger, so 2.67. If you do for this other community 5, 6, 7, 8, you see here everybody is connected to everybody else, right? In 5, 6, 7, 8. So you're going to have all positive modularity scores. So the sum is going to be also larger. Okay, so there's a name. If all the vertices in a community are connected to every other vertex, then that is also called a clique. I've heard of this called clique.
Yes.
Okay, so they say people move like a clique, which means they move together as one community. Okay, so a clique is the best possible community you can have because every vertex is connected to every other vertex.
So here the picture difference is like means the user means we has to remove the links or it's already.
No. So here, so the algorithm is going to give you, okay, the communities are 1, 2, 3, 4, and 5, 6, 7, 8. So here I have drawn just for our visualization purpose, just the edges between vertices within the community. So 5, 6, 7, 8. In the given graph, yes, there are edges between any two vertices within 5, 6, 7, 8. Whereas 1, 2, 3, 4, these are the edges between involving 1, 2, 3, 4. The previous case involving 1, 4, 5, 7, these are the only edges. Involving 2, 3, 6, 8, these are the only edges. So which means if you look at this, majority of the edges in the graph are between communities. You see you have edges between 7, 8, you have between 5, 8, you have between 6, 7, you have 4, 6, you have between what, 3, 4. Yeah, so a lot of edges between communities. Is that clear? Okay, that's not a good partitioning. It means what? Like, think about people, communities means people talk more among themselves within the community rather than talking outside other communities. But with this partitioning, it looks like there are people talking across two communities. That is more common compared to people talking within the communities. Right? So if you go ahead and determine as a practice the internal density and the external density for this partitioning, you will find the external density to be actually higher compared to, and the internal density may actually be lower. Okay, so that's another way of evaluating how good is this partitioning. So that is also showing up in the modularity score. You see here, the modularity score for this community is 2.67 and for this is 2.87. So the sum of the two modularity scores is 5.54. Okay, so this is a reflection of how good is this partitioning. So if you want to decide which to choose, this partitioning or the previous one, you will choose this one because it has a larger total modularity score of 5.54 compared to what, 0.46 is the total modularity score. Is that clear? Okay, so that is how you could evaluate how good is a partitioning of a graph into communities.
Means now what is the use of this? We will means what is the use of this?
Okay, so this is the same graph we did consider, right? So one algorithm. So as I said, there are different algorithms out there to do community detection. So one algorithm says, okay, this is the partitioning. 1, 4, 5, 7 is one community. 2, 3, 6, 8 is another community. Another algorithm says this is the partitioning. 1, 2, 3, 4 and 5, 6, 7, 8. So you want to know which of the two to choose. So you compute the modularity scores and decide which one to choose.
Oh, for the same.
For the same graph. You have different algorithms that could possibly give you different communities based on the approach they use.
Got it.
Okay?
Got it.
Okay, so now let us see the actual community detection algorithms. So we are going to see what is called this hierarchical clustering. So hierarchical means we'll try to show like a partitioning hierarchy of the graph into different partitions. So then we are going to come up with modularity scores for each of these partitions. So we're going to kind of partition the graph into different communities and kind of decide where to cut it off, whether to cut off like this or cut off like this, and decide what is the best possible partition. Okay, so that's the idea. Now we could do, as the name is indicated here, bottom-up approach. This is what you're going to see is called a bottom-up approach, and one example for that is a complete linkage clustering algorithm. Then we'll see the top-down approach, okay, based on edge between and centrality. So let us see first this bottom-up approach. So what a bottom-up approach means is, we are going to start with individual vertices as communities on their own, and then you're going to combine. So it's like building from the bottom all the way to the whole graph as one community. Okay, so that's the bottom-up approach. Okay, so let us see this with an example. So the first step with this approach is to compute the distance matrix. So you all know how to get the distance matrix, isn't it? What's the distance matrix? It has the what? Number of edges on the shortest path between any two vertices, right? So this is the graph 1, 2, 3, 4, 5, 6. And so you write down the distance matrix like this: 1, 2, 3, 4, 5, 6 rows and columns. And it's a square, symmetric matrix. So which means you just fill the upper diagonal. You don't need to fill the entire matrix. Okay. So from a vertex to itself, it is all zeros. Okay. Then from 1, you can reach 2 on a shortest path of one edge. So you have a 1. Similarly, 1, 2, 3, you have one edge. Then 1 to 4, you have 2 edges. Then 1 to 5, you have 2 edges. Then 1 to 6, you have 3 edges. Okay? So that's the shortest path between from one to every other vertex. So similarly, you find the shortest path from each vertex to every other vertex. So if it's a larger graph, you could use the breadth first search algorithm. For smaller graphs, you just visually look at it and find the number of edges in the shortest path. Okay? So from 2, just look at 3, 4, 5, 6 because it's symmetric. You don't need to look from 2 to 1. It's already accounted for here. So 2 to 3 is one edge, 2 to 4 is also one edge, 2 to 5 is 2 edges, and 2 to 6 is also 2 edges. So like that you find the shortest path or the number of edges in the shortest path between any two vertices. I won't say it, just running. Okay. So we found the distance matrix, right? So now we are going through a sequence of iterations. Okay, so as I said, we are going to start with each vertex on its own community. And then we're going to combine in each iteration two communities to one community. So which two communities we are going to combine is what we need to decide for each iteration. Okay. So to begin with, we just have 1 on its own, 2 on its own, 3 on its own, and so on. Okay. All right. So this is kind of the initial matrix. Okay. We'll keep that matrix also for some other purposes later. So the first iteration. So in each iteration, we'll pick the smallest entry in the distance matrix. Now, if the smallest means lowest value. So if the lowest value is occurring multiple times, like here, we have multiple occurrences of 1. Of course, we don't pick 0 as the lowest value because that's from a vertex to itself. So non-zero value. So we have multiple occurrences of 1. So we need to look at between what communities those values are, the lowest values are. So again, as I said to begin with, we can consider each vertex in its own community. Okay. So if you notice, all the ties are between a vertex-vertex pair, right? Between one vertex and another vertex. Later, we'll have ties between a cluster or a community and a vertex. So that's a cluster vertex pair. So like in this case, you have the lowest score of 2 between a cluster and a vertex. Another cluster and a vertex. So you have a cluster vertex pair, a cluster vertex pair. So there we have to deal how to break the ties between two cluster vertex pairs. Sometimes you could have ties between a cluster vertex pair is one entity and the other entity could be a vertex-vertex pair. So we'll see scenarios for that. So there are 3 possibilities. Okay. So I have written down the tie breaking rules for each possibilities here. Okay. So right now we are seeing a tie between two vertex pairs, two or more vertex pairs. So in that case, just break the tie arbitrarily. So which means you could, so we are going to combine, as I said, two communities to one community. So you could pick any two vertices or any two communities, okay, and combine them. So we'll just combine the first two vertices, 1 and 2. Okay. So once we combine 1 and 2, we need to come up with a new distance matrix that has 1 and 2 together as one entity. So 1 and 2 are no longer separate vertices or entities, they are considered together as one entity. So we need to write the distance matrix that has 1 and 2 together, then 3, 4, 5, 6.
So why 1 and 2?
Because we're combining them to one community, so they are like one entity now. Okay.
Why we can't?
We can combine 3 and 4 also.
1 and 3. But
You can do 1 and 3 because when there's a tie between vertex pair, you can choose anything to combine arbitrarily. So just as a convention, we'll pick the first two. Okay, 1 and 2. You can do 1 and 3 and see what happens. Okay. All right. So again, the diagonal is going to be 0. So 1, 2 with 1, 2 is going to be 0. 3, 3, 0, 4, 4, 0, 4, 5, 5, 0, 6, 6, 0. So now we need to fill this entry 1, 2 with 3. So for that, what you need to do is, so looking at 1, 2 with 3. So go to the original distance matrix. Find the pairwise distances between the entities involved. So here you are looking at 1 and 2 as one cluster and 3 on its own. So find the pairwise distance between vertices in each cluster. So you have 1, 3 is a pair, 2, 3 is a pair. So 1, 3, the distance is all 1 and 2, 3 is also 1. So look at this block of values. Okay? So pick the maximum among them. So the maximum distance between any two pairs or any two vertices that are part of the two entities will be the value that goes here. So it is also 1. Is that clear? So do the same thing for 1, 2 with 4. So 1, 2 with 4, you have this block, 2 and 1. So the maximum is 2. So that's the value that should go in this distance matrix. Is that clear? Then 1, 2 with 5, what should be the value? You have 2 and 2. So the value that should go here is 2. Then 1, 2 with 6, you have 3 and 2. So you should take the maximum of 3 and 2. So that's going to be 3.
So why we are considering maximum value?
Because you are looking at the pairwise distances. So you want to again, when you, as I said, when you combine vertices to communities, right? So you want to bring vertices that are having an edge to each other or closer to each other. So the maximum distance between, so if I put 1, 2 and 6 as one community, is that clear? If I put 1, 2 and 6 as one community, what is the maximum distance between any two vertices within that community? If I put 1, 2 and 6 as one community, between 1 to 6 the distance is 3. So you have to go through two other vertices to reach 6. 1 and 2 of course are connected to each other. Then 2 and 6 you have 2 edges. So this is how actually the edges are. Right, so we want to know what is the maximum distance between any two vertices within the community, and you want to minimize that, or you prefer a minimum value.
I got it.
Okay. All right. So that's the distance entries here. So now 3 with 4, 3 with 5, 3 with 6 we can get from the same original matrix. They don't change. The 2, 1, 2. They are just coming out as it is. Is that clear? Because you're not combining 3 with 4 or anything, so they are not touched yet. So we can just use their value. Similarly, 4 with 5 and 6. We didn't do anything with 4, 5, 6. So whatever was the previous value, they can come as it is. Similarly, 5 and 6 we did not touch them. So these are the entries in the distance matrix after the first iteration. Is that clear? Okay. So now we need to proceed with this as the basis. So now we need to again pick the smallest value and see if there is any tie, we need to break the tie. So let us see. So this one is between a cluster vertex pair. So this is a cluster now, and this is a vertex. So this one is involving a cluster vertex pair, whereas this one is involving what? A vertex vertex pair. This one is also between a vertex vertex pair, and this one is between also a vertex vertex pair.
Even the value is 1, that's why you are taking it?
Huh? Yeah, the smallest value.
Okay.
So we need to now combine two communities to one community. So which two communities we need to pick?
So,
The smallest value, which is of distance 1, right? So it means what? The one, this
distance.
community and this community, the distance between them is 1. So we want to combine those two communities as one community, rather than combining two communities that have a distance of what? 2 or 3. Because that would make them not really a close community. They are like far from each other. Is that clear? So that is why we would prefer to always pick the smallest value in the distance matrix and combine those two communities as one community. Okay? So we need to now decide. We have one cluster vertex pair and 3 vertex vertex pairs. So the rule is, if you have ties between or involving cluster vertex pair and a vertex vertex pair, in case of a tie between a cluster vertex pair and vertex vertex pairs, choose the cluster vertex pair. So we have only one cluster vertex pair and 3 vertex vertex pairs. So we'll just go with the cluster vertex pair, which is what? What's a cluster vertex pair here? 1, 2 with 3. So we are going to combine 1, 2 with 3. So as you do the iterations, draw the hierarchy. So we have combined so far 1 and 2. So now we decide to combine 1, 2 with 3. So 1, 2, 3 are one community now, or they exist as one entity in the distance matrix. So the distance matrix for now, this new iteration is going to be 1, 2 and 3 as one community, then 4, 5, 6 as usual. Then so 1, 2, 3, 4, 5, 6. So we'll fill the diagonal with zeros. Okay. So now we need to decide what should go for this 1, 2, 3 with 4. Is that clear? So again we need to go to the original distance matrix. So don't make the mistake of going to the other matrix. So we need to decide the maximum distance between 1, 2, 3 and 4. So we have to look at this block of vertices or the values, the distance values. So between 1, 2, 3 as one entity and 4 on the other side, what is the maximum pairwise distance? Okay, so that's going to be what? Maximum of 2, 1 and 2 is 2. So that's going to be the value. Is that clear? So between 1, 2 and 3 on one side and then 4. So across the two communities. Similarly 1, 2, 3 now is 5. It's going to be
2.
This block, so it's going to be 2. The other block is going to be 1, 2, 3 is 6, it's going to be 3. So we have 2 and 3. Is that clear? So that's how you come up with the values. Any question on this? So now 4 with 5 and 6. So 4, 5 we did not change. So whatever the value, 2, 1 and then 5, 6 is also 1. So you see the number of entries in the distance matrix reduces by 1 each time, the number of rows and columns. We started with 6 rows, 6 columns, 6 vertices basically, or 6 entities. Now we have 5, now 4. Right? So 1, 2 and 3 are combined as one community. So let us proceed further. So we now need to look for the smallest value in this distance matrix, which is 1, 1. So we still have time. So we need to find what entities are part of this one. So this one is between what? The vertex path. And this one is also between a vertex path. So there's tie between two vertex paths. So how would you break the tie? Arbitrarily. You could pick any vertex path, right?
Yeah.
The vertex path we don't need to worry about. Just make one vertex path. So you could pick 4, 6 and combine them, or 5, 6 and combine them. It's up to you. So we'll pick 4 and 6 to combine. Okay. So you have to write the new distance matrix that has 4, 6 as one cluster. So 1, 2, 3 as one cluster, then 4, 6 as one. So the remaining one is 5. So now you have 1, 2, 3, 4, 6, and 5. So you have 0, 0, 0 as the diagonal. So now we need to look at 1, 2, 3 with 4, 6. So again, pairwise distances. So 1, 2, 3 with 4, 6. What is the maximum distance between all these pairs? 1 with 4 and 6, 2 with 4 and 6, 3 with 4 and 6. So you have different combinations. So what is the maximum of all those pairwise distances? Is that clear? So we need to look at what? We have 1, 2, 3 with 4. So this block combined with 1, 2, 3 with 6. So this block. So you have 2, 1, 2, 3, 2, 2. So what's the maximum? 3. So that should be the value that go here. 1, 2, 3 with 4, 6. This is the maximum of the entries in the block. So 1, 2, 3 is 5. This one. 1, 2, 3 is 5 is going to be 2, 2 and 1. So that's going to be 2. Now 4, 6 with 5. So how to decide that? So 4, 6 with 5. So pick up 5 and 4 and 6. So 4 with 5 is 2. So 4, 6 with 5. So you need 4, 5 and 5, 6. So 4, 5 is 2. 5, 6 is 1. So you need to pick the maximum of 2 and 1. Is that clear? 4, 6 with 5. So 4, 5 and 5, 6. So the maximum is 2. Right? So we are combined 4 and 6. So now the smallest value is 2. So the 2 is between what? This is a cluster vertex path. And this 2 is also between a cluster vertex path. So you have a tie between two cluster vertex paths. So that's the third possibility. So how to break the tie between two cluster vertex paths? Okay, so I'll tell you the method and then I'll read this statement. Okay, so the way we break the tie is
Individual.
what?
Individual. You need to do it individually.
Yeah, find the individual distances, add them up. So you have 1, 2, 3 with 5. So this is one cluster vertex path. So we need to find the distance from 1 to 5, 2 to 5, 3 to 5 from the distance matrix, add them up and divide by what? The total number of vertices. So if you want to put all those entities as vertices as one community, you have 4 vertices total, right? So we need to find the distance from 1 to 5. The distance from 1 to 5 is 2. Distance from 2 to 5 is also 2. Distance from 3 to 5 is 1. So the sum of these values, what is that? 2 plus 2 plus 1. Right? So the distance from 1 to 5 is 2 from the original matrix. 2 to 5 is also 2. 3 to 5 is 1. So the sum is 2 plus 2 plus 1 divided by 4. So again, why 4? Because totally there are 4 vertices involved if we combine them to one community. So that's going to be 1.25. Okay? The other cluster vertex pair is what? What's the other cluster vertex pair? 4, 6 with 5. So 4, 6 with 5. What is the pairwise distance here? 4, 5, the distance is 2. 5, 6, the distance is 1. So what should be the this average? You can call this as what? Pairwise distance divided by pair size.
3 by 3.
3 divided by 2 plus 1 divided by 3. Why 3? Because the 3 vertices totally. So this pair distance pair size ratio is 1. So between the two cluster vertex pair, you would want to pick that pair that has the smallest value for this ratio, for the distance size ratio. The reason why we go for the smallest is, if you look at this, overall this is like, this looks like a more compact cluster compared to these 4 vertices, because you have 2 pairs with the distance of 2 between them, 2 edges between them. Whereas here there's one pair at the distance of 2 and another pair at the distance of 1. So this pair is relatively more compact or closer to each other compared to this one. And it is also quantified based on this ratio. So we go with the smaller value, the pair that has a smaller value for the ratio. So that's the third rule or third possibility to break the type. So if you read out this statement here, choose the pair with the minimum value for the total pairwise distance. So that's the total pairwise distance in the numerator divided by the sum of the 2 pair sizes. So sum of the 2 pair sizes means here 3 plus 1, 4 is the total pair size. And the sum of the pairwise distances. Here it is 3 is the total pair size. Numerator is also 2 plus 1, 3. Okay? So which means you're going to combine 4, 5 and 6 as one community. So we have only 2 communities now, 1, 2, 3 and 4, 5, 6. So that's the maximum we can do. Then the next would be to just combine the 2 communities to one community, which is the whole graph. So which means we have a hierarchy like this. 1 to 6, the entire graph considers one community. Then we have 1, 2, 3 as one community, 4, 5, 6 as another community. Then how was 1, 2, 3 built up? From 1, 2 and 3. And 1, 2 came from 1 and 2. Then 4, 5, 6 came from 4, 6 and 5. And 4, 6 came from 4, 6. So this is the partition hierarchy. So now we need to decide where to actually partition. Okay? So for that we'll make use of the modularity scores. So you have the pairwise modularity scores that you can get, right? So if all the 6 vertices are considered as one community, what is the modularity score? So how do you find that modularity score? In your the Java program is going to give all these pairwise modularity scores, isn't it? So now, since it is all the vertices considered together, we just need to add all these values, because 1 through 1, 2, 3, 4, 5, 6 together as one community. So these were the possible pairs. Just add all the modularity scores. There are some negative values, there are some positive values. Negative because that pair don't have an edge between them. So the total modularity score is 1.21. Now do the same thing for each community. So 1, 2 and 3 as one community. So what pairs you have to consider for the modularity score? If it's 1, 2 and 3, what are the pairs? What did we do in the examples earlier? Just consider all possible combinations. If it is 1, 4, 5, 7, consider 1, 4, 1, 5, 1, 7, 5, 4, 5, 4, 7 and 5, 7. So all combinations of vertices. So we have the pairwise modularity scores for all of them, for all combinations from the output from the program. So for 1, 2 and 3 you will consider 1, 2 as a pair, 1, 3 as a pair, 2, 3 as a pair. So these are 3 pairs, possibly 3 vertices. Clear? So find the modularity score. So 1, 2 it is some 0.57, 1, 3 is another 0.57 and 2, 3 is 0.357. So add up all those 3 modularity scores. So that is 1.50. Okay? Similarly, for this community 4, 5, 6, what are the pairs we need to consider?
4, 5.
4, 5, 4, 6 and 5, 6. So add the 3 modularity scores corresponding to those 3 pairs. The sum comes out to be 1.14. Okay? So now we need to decide whether to keep, we'll go level by level. So we saw the whole thing as one community, the modularity score is 1.21. If we partition them to 2 communities, we get like this. So we need to now decide whether to keep the whole graph as one community or partition them like this. So we did something like that before also, the eigenvector based approach. So what did we do there? We need to look at whether the modularity score is improving with the partitioning. So when we break into 2 communities, the total modularity score is 1.5 plus 1.14, which is like 2.64. It is larger than 1.21. So if they exist together as one community, the modularity score is 1.21. If we break it down, the total modularity score is 2.64. So the modularity score is actually improving. So we decide to break down to 1, 2, 3 as one community, then 4, 5, 6 as another community. So now we need to decide whether to proceed further or not. So according to the partition hierarchy, we have 1, 2 as one community and 3 on its own. So if a vertex is on its own community, the modularity score for the community is 0. Okay? Then the modularity score for 1 and 2 is a fraction, always going to be less than 1. So like it is 0.57. So 0.57 plus 0 is 0.57, and that is less than 1.50. So which means, should we break this down into 2 partitions like this, or should we keep 1, 2, 3 together? 1, 2, 3 together as one community. So we decide to stop here. Okay, so that's, we don't want to proceed further, so we can just what is called prune. Okay, so you might have heard of this pruning technique, so in machine learning. So we'll find the overall partition hierarchy and then prune it. Now, with 4, 5, 6. Again, according to our hierarchy, if you partition it, it has to be like 4, 6 as one community and 5 by itself. Again, 4, 6, the modularity score is 0.71, 5 is 0. So the sum is going to be 0.71 less than 1.14. So we just decide to stay with 4, 5, 6. Okay? So that is the final partitioning. We don't want to go further down. So we can show something like this. This is the final partitioning. So this sum of the modularity scores of the final communities is 1.50, 1.14, so it's 2.64. It's the total modularity score. Okay? And you can also show something like this. Okay, so these are the 2 communities, and you have some edges across the communities, and this is actually a click, 1, 2, 3. They have edges between themselves. And you have 4, 5, 4, 5, 6. There's no edge between 4 and 5. Okay? Is it clear? Any question? So there is another graph that you can actually practice. So this is the graph that we will use most of the time throughout this module to compare the algorithms. So again, what's the first step? Come up with a distance matrix, right? So you know how to get a distance matrix. So then proceed through the iterations. So the distance matrix, you choose the entry with the smallest distance value. So the one here, and there are several such ones. So and then all the ones are between vertex pair. So you can choose any vertex pair to combine. So just combine 1 and 2. So the key thing is once you combine two vertices or two entities, two communities, you need to find the distance involving the cluster, and the other side could also be a cluster or a vertex. So in this case, you combine 1 and 2. So we need to find the distance between 1, 2 as one entity with 3, 4, 5, 6, 7, 8. So 1, 2 with 3 is going to be the maximum of the values in this block. 1, 2 with 3. So that's going to be 1, right? 1, 2 with 4 is going to be this. Similarly, 1, 2 with 5 and so on. So 1, 2 with say 7 is going to be the maximum of 3 and 2. Is that clear? So we combine 1 and 2. Alright, so again now you have several ones, but as before, all the other ones out here are between a vertex pair, and this one is between a cluster vertex pair. So we break the tie by going for the cluster vertex pair. So which means you will combine 1, 2 and 3 into one cluster and go further. So when you combine 1, 2, 3 as one cluster, the distance between 1, 2, 3 and 4 has to be based on the distance values in this block and so on, okay? So the 1, 2, 3 has one entity now with 4, 5, 6, 7, 8. Okay. Now you have several ones, and all these ones are between vertex pairs. 4, 5, 4, 6, 5, 6, 5, 7, and so on. So you can break the die how? Arbitrarily. So just pick 4 and 5. So combine 4, 5. So now to find the distance between 1, 2, 3 and 4, 5, what do you have to do? Go to the original distance matrix. So 1, 2, 3 with 4 and 5. So 1, 2, 3 with 4, 5. So this is the block. Okay? So make sure 1, 2 and 3, all the 3 vertices, and 4, 5. So the maximum of this block is 2. So that is the distance value that should go here. 1, 2, 3 with 4, 5. Similarly, 4, 5 with 6, you have to find the maximum distance between 4, 6 and 5, 6. So whatever is the maximum distance between the two, that goes here. So now we have this distance matrix. So you have again some ones. So notice here, this one is between what? A cluster vertex pair. What about this one? It's between a 6 and 7. That's a vertex pair. This is between a vertex pair, right? So which one you should go for to combine?
Close to vertex.
A cluster vertex pair. You have a cluster vertex pair and two vertex pair. So you always prefer the cluster vertex pair. If there are multiple such cluster vertex pairs, then you have to break the tie by doing what? Like this. Add the pairwise distances divided by the sum of the pair sizes. Okay, so we'll decide to combine 4, 5 and 6 together as one community. So 4, 5, 6. So again, to find the pairwise distance between 1, 2, 3, 4, 5, 6, what we have to do? Go with the original distance matrix. So 1, 2, 3 with 4, 5, 6. So these are the values we need to consider. And pick the maximum among the values in this block, which is 2. Okay? So just always go to the original distance matrix. Okay, so we still have a 1 here now, so which is 7, 8. That's the only lowest value, so we could combine 7 and 8. So again, to find the distance between 1, 2, 3 with 7, 8, what you should do? Find the maximum of the distance values 1 to 7, 1 to 8, 2 to 7, 2 to 8, 3 to 7, 3 to 8. So that maximum value should go here, which is 3. So this is the new distance matrix. You have to find the minimum, which is 2. So there's a tie. So this tie is between what? This 2 is between a cluster pair. And this is also a cluster pair. So we need to do something like that. Okay? So let's do that. So 1, 2, 3 with 4, 5, 6. So we need to really sum up all those distance values in the block. 1, 2, 3 with 4, 5, 6. Okay? So that's going to be 1 plus 2, 2 is 5, 10, 4, 14. So 14 divided by what? 6. Why? Because there are 6 vertices together in the 2 pairs put together. So 14 divided by 6 is one value. What is the other pair? Cluster pair. 4, 5, 6 with 7, 8. So 4, 5, 6 with 7, 8 is going to be what? 4, 5, 6 with 7, 8 is going to be this. So that's going to be 2 plus 2, 4, 6, 8. So 8 divided by again how many vertices? 4, 5, 6, 7, 8. 5 vertices. Okay? So that's going 14 divided by 6 is going to be some 2 point something. 8 divided by 5 is going to be 1.6. So which is smaller? This one. So we'll combine 4, 5, 6 with 7, 8. Okay, so that's the way to combine. So 4, 5, 6, 7, 8 and is one cluster. 1, 2, 3 is the other cluster. So this is the partitioning hierarchy. So now what we need to do, once we have this partitioning hierarchy, we need to decide where to stop, right? So again, run the pairwise modularity scores, the Java program, get the pairwise modularity scores, find the modularity score for all the 8 vertices as one community. Typically that will come out very small because we don't have edges between all pairs. And then for each of these communities. So if you want to do it for 1, 2 and 3, what pairs you need to consider?
1, 2,
1, 2, 1, 3, 2, 3, all combinations. Similarly 4, 5, 6, 7, 8. 4, 5, 4, 6, 4, 7, 4, 8, then 5, 6, 5, 7, 5, 8, and so on. So add all the pairwise modularity scores. So that will come out to be, so I have all the pairwise modularity scores. So that comes out to be 2.73 and then 1.9. So the sum 2.73 plus 1.9 is going to be greater than 1.97. That's the modularity score for the whole graph as one community. So we decide to partition 1 to 8 as 1, 2, 3 and 4, 5, 6, 7, 8. Is that clear? We'll finish it up quickly. So now we need to decide whether to partition 1, 2, 3 further. So if they have to be partitioned, it's going to be like 1, 2 and 3. So 1, 2 is something less than 1 and 3 is 0. So the sum is going to be less than 1.9. So which means we don't want to proceed further. Just stop at 1, 2, 3. Is that clear? So now we need to decide about 4, 5, 6, 7, 8. So if at all we partition, it's going to be 4, 5, 6 and 7, 8. 7, 8 is just one pair, so that is 0.70. 4, 5, 6 is like what? 4, 5, 4, 6, 5, 6. So add all the 3 pair values, pairwise modularity scores, it comes out to only 0.83, which means there could be some pairs without edges. So what do you decide, whether to break it up or just stay the whole thing as one community? Stay. Why? Because the sum of 4, 5, 6 is 0.83, the 7, 8 is 0.70. The sum is going to be 1.53. It's less than 2.73. So we just decide to stop partitioning. Just stay with this. Is that clear? So practice problems like this.